right, so just this morning, the APPhysics C Electricity and Magnetism 2025 free response questions have been released, at least for, it says version J here. So we'll actually go through these one problem at a time. And maybe if you took the exam, see how you did. First, we have an isolated air-filled charged capacitor that consists of two conducting coaxial cylindrical shells that each have length L. The inner shell radius R1 and the outer shell has radius R2, as shown in figure 1, where R1 and R2 are much less than the length, which means that you can essentially assume that this is an infinitely long cylinder. That may help us to use Gauss's law to derive expressions for the electric field. And you also have surface charge densities for both the inner and outer shells. The absolute values of the total charges are equal. So they're equal and opposite charges. And as it says, use Gauss's law to derive an expression for the magnitude E of the electric field as a function of radial distance R from the center of the capacitor. For the region R is between R1 and R2, express your answer in terms of R1, sigma 1, and little r, and physical constants as appropriate. So as I mentioned, you'll be using Gauss's law to derive the electric field inside of this coaxial, what is essentially an infinitely long cylinder. Now, this is the coax cable. Our Gaussian surface will be drawn essentially to be a cylinder that is between these two, right? The radius, little r, is between the inner and outer radius of the coax cable. And so the only charge that will be contained inside is based on the positive sigma 1, which is why they're telling you to express that in your answer. Now, what does Gauss's law say? Gauss's law says the integral of E dot dA is equal to the charge inside over epsilon naught. Now, because it's a Gaussian, one of the special Gaussian surfaces, being either a plane, infinitely long cylinder, or a sphere, we can simply write this as EA. It's a charge inside over epsilon naught. Now, what is the area of the cylinder? Well, that's just going to be the circumference 2 pi r times the length. That'll be E times 2 pi little r L, because little r represents the radius of the inner cylinder. That'll be equal to the charge inside, which we said was, let's see, these are expressed as densities. They are surface charge densities. Now, the charge inside, what is that going to be? That's going to be the charge density given to us, rho 1, times area of the charged object, which is not the same as the area of the Gaussian surface. The Gaussian surface has little r. This one's going to be R1. It's based on the geometry of the inner coax here. So that'll be sigma 1 times 2 pi R1 L. And so you're going to see, when we solve for E, a bunch of these terms, or I should say factors, will cancel. The 2 pi's cancel, the lengths cancel. And so finally, the magnitude of the electric field, which will be going radially outward as the electric field points from positive to negative charge distribution, will be sigma 1 times the ratio of R1 over little r epsilon naught. So as you can see, it's expressed in terms of big R1, sigma 1, and little r, along with physical constants. Next, they want us to derive an expression for the absolute value of the voltage difference or potential difference between the outer and inner shells R1, R2, and sigma 1, along with physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or equation from reference information. I'll go ahead and do that in the space below. So the voltage difference, it's similar to potential energy. Find potential energy, you can integrate force over distance. So with potential, we integrate electric field over distance, this being the radius, radially outward. We have to integrate here, especially because the electric field is not constant with respect to radius. So we're going to integrate this and get a natural log, because we're going to be integrating sigma R1, R is in the denominator there. This whole expression will go inside Where are we integrating from? We want the potential difference between the inner and outer shell, so we'll integrate from radius 1 out to radius 2. So this will go from R1 to R2 dr. Now, sigma 1, R1, and epsilon naught, those are all constants with respect to the variable of integration, so those can all be pulled out. That'll leave us with integral of 1 over r, which becomes the natural log of r from R1 to R2. Now, if you remember with natural logs or any logarithms, we'll have ln R2 minus ln R1. If you subtract two logs, that becomes a quotient or dividing on the inside. So the absolute value of the voltage difference, we're going to want to have R2 in the numerator, that's the larger one. That'll be sigma 1 R1 over epsilon naught, natural log of the ratio of the two radii. That's the answer for part 2. Now for part 3. On the axes shown, sketch the graph of E, its magnitude, as a function of R from 0 to the position that is outside the outer shell. All right. So note that it says surface charge density. That means that the charge exists only on the surface. So ultimately what that means is that the electric field inside of the inner coax will actually be 0 because there's no charge in there. If we form our Gaussian cylinder at a radius less than R1, we enclose no charge. There's no charge inside of this region, as you can see. It's only on the surface. So that means that the electric field at radii less than R1 is 0. Then all of a sudden, I have encapsulated that, that sigma 1 charge once I'm out here. Now it goes from containing no charge to containing all of the charge that lies on the inner coax. So it's going to go ahead and jump up to some value. We said that EA is equal to charge enclosed over epsilon naught. E is equal to charge inside over A epsilon naught. Well, charge inside over A, that's just the density of the inner coax, charge per unit area over epsilon naught. This will be charge enclosed over epsilon naught, and we have an inverse relationship with R, so it will start looking like the graph 1 over x, where it decreases inversely. Then once we get to the outer radius, note that these two charges are equal and opposite, so they'll cancel, meaning the net charge enclosed is 0. So that the electric field outside of the coax will also be 0. So your graph should look something like this. Now they've thrown in, instead of air, some material of dielectric constant K inserted between the two coaxial cylinders. So remember that the dielectric constant allows you to increase the capacitance. It's a linear relationship, so say your dielectric constant is 2, then you have twice the capacitance as you would without it. Derive an expression for the capacitance C of the capacitor with the material being inserted in terms of length R1, R2, and K. So you remember the definition of capacitance is equal to charge divided by the potential difference between the two plates, in this case the coaxial cylinders. Now what we're going to have to do is actually multiply by K once we get this initial expression. What we'll do is we'll call this like the initial capacitance, assuming that there's no dielectric in between. And once we get this expression, we will multiply it by the dielectric constant. So, of course, we're not going to be able to have Q or charge in the answer. Usually the capacitance just depends on the geometry of the capacitor itself. So we need to get an expression for the charge between the two plates, which we've already done that. As you notice, we've already gotten the expression for the potential difference between, which involves sigma 1. So my expression for Q should also involve sigma 1. Why? Well, that'll give me sigma 1 on the top and sigma 1 on the bottom. They'll cancel so that I don't have my answer in terms of sigma 1. Notice that I'm not allowed to express the capacitance in terms of that. So if you remember what the charge is, the charge plus or minus is both the same. We could just use sigma 1 times the surface area of this, which was 2 pi RL. So it'll be sigma 1 times 2 pi R1 L all over the expression that we just derived for the capacitance, sigma 1 R1 all over epsilon naught, sigma 1 R1 all over epsilon naught, ln of R2 over R1. That will allow the sigma 1s to cancel, the R1s to cancel, and that's all that cancels, 2 pi epsilon naught L over the natural log of R2 over R1. Oh, and remember, that's going to be our capacitance when we don't have the dielectric in. So we have to multiply by K to get the final answer. So the full capacitance will be K times 2 pi epsilon naught L over ln R2 over R1. So next we have what looks like a magnetic induction or Lenz's law problem. A rotating circular conducting loop of area A and resistance R is in an external uniform magnetic field that is directed in the negative Z direction, which is into the page. At time t0, the magnetic field is perpendicular as shown. The loop is rotating with constant angular speed omega and period t about the dashed line shown that is along the diameter. So we have the magnetic flux over time. They actually were friendly enough to give that to us. Usually it's the dot product of A and B, so AB cosine theta, but now instead of theta, it's omega t because the angle is changing over time because the ring's rotating. The absolute value of the induced EMF in the loop is absolute value of V. The partially completed bar chart shown represents E at a quarter of the period, Draw the bars to represent E at times T0, 1/4 T, and 1/2 T. Okay, well, let's think of this in terms of EMF, which, if you remember, induced EMF is equal to negative change in magnetic flux over time. And again, they were fortunately kind enough to us to give us the expression for what magnetic flux is. So usually one of the three quantities is changing that you have involved. Either the area is changing, the magnetic field strength is changing, or the angle is changing. And so in this case, it is the angle. So you can just simply take the derivative of that expression with respect to time, dA cosine omega t. So if you take the derivative with respect to that, we only care about the absolute value, by the way. So the negative sign won't really end up mattering. That's going to be BA, and so you'll have negative sine omega t, and due to chain rule, you also have to multiply by omega. So the absolute value of this is going to be omega BA sine omega t. That is the induced EMF. So because it's sinusoidal and everything else is going to be constant, it just depends on the time. It's going to be like a sine wave. So at time 0, we're going to have no induced EMF, assuming nothing's changed yet from the beginning. Then so if you remember drawing, sine graphs, this is one period, this is t, this is half of the period. So you're actually back at 0 again. And then these are both max and min amplitude, positive and negative. So when you're at a quarter of the period, you're at maximum displacement, and at 3/4. So these are actually equal and opposite, but because it's absolute value, these will both be the same. So you have 0 EMF zero EMF, and then the at 1/4 of the period and 3/4 of the period, these quantities will both be the same. Oh, they say write a 0 in that column, so I'll just write 0. Right. Derive an expression for the maximum induced current in the loop in terms of A, R, B, omega, and physical constants is appropriate. Begin your derivation by writing a fundamental physics principle or equation. So they want the expression for the induced current. So again, we can get that from the induced EMF that we just did earlier, actually. That's just going to be the absolute value of the derivative of magnetic flux over time, which we already did that, actually. It was omega BA sine omega t. And they care about the max induced current. That's fine. It doesn't really depend on the sign. So this is the EMF or voltage. So how do we get the current? If we have the voltage, we just use Ohm's law. Current is equal to V or EMF over R. So if I want I, the current, I would just take this expression and divide by the resistance. Now they want the maximum. Okay, well, if it's some number times sine, the maximum is just going to be that number, right? The maximum value for sine is equal to 1. So that just means that I max, the maximum current, will be the maximum possible EMF, omega BA, over R. Omega BA over R. And as you can see, it uses A, R, B, and omega, and we don't need any other physical constants. On the axes shown, sketch a graph of the instantaneous power dissipated by the loop as a function of t. How do we get an expression for power? It's I times V. Or in this case, I times the EMF. So to get the expression for that, we have an expression for I, we have an expression for E. It might be easier to think of this as I squared R. So we'll just take this expression up here, square it, and multiply by R. That's going to give us omega squared, E squared, A squared, sine squared, everything's squared here. We would have R squared on the bottom, but remember we multiply by R, so now it's going to be over R. So this is going to be sine squared. So sine squared is going to reach its maximum at 1/4 and 3/4. It's going to be 0 elsewhere. 0, 0, and 0. So it's going to look something like this. With that upper amplitude being the omega squared, B squared, A squared over R quantity. So this is the instantaneous power in the loop over time. Indicate whether your sketch you drew in part C is consistent with the bars you drew in part A. Briefly justify your answer by reflecting the functional dependence between the power and epsilon. So if you refer back to the chart, we said that there was 0 EMF. Well, how do we relate EMF to power? Well, as we said earlier, power is equal to IV, which can also be expressed as I squared R, or even equal to V squared over R. I like the idea of expressing it as V squared over R because R is a constant. The resistance is not changing. So we know for sure that if the EMF is 0, then the power is 0. Well, where's the power 0? At time 0, half the period, and full period t. And you can see at time 0 and half the period, it is the EMF is 0 as well. And if the EMF is 0, the power is 0. And again, EMF is maximized at 1/4 and 3/4 of the period, which we can see here. This is 1/4 of the period, and this is 3/4 of the period. So it is consistent with our derivation in the previous parts of the problem. So next up is question 3. In experiment 1, that implies there may be multiple experiments going on in this problem. Students are asked to use a graph to determine the resistivity, row 1, of a circuit element that is connected to a variable power supply as shown in figure 1. The circuit element is cylindrical and has uniform density, so it has some cross-sectional area, pi r squared, or uniform resistivity, excuse me. The students have access to a voltmeter, okay, so they can measure voltage, an ammeter, so they can measure current, and a ruler, so they can measure length. So this formula, if you remember, the resistance is equal to resistivity times length over area, may be helpful to us. Let's write I for current. Okay. Describe a procedure for collecting data that would allow the students to use a graph to determine row 1, including any steps necessary to reduce experimental uncertainty. We have to think about what the dependent and independent variables could be. What could they be manipulating? Well, based on this equation, if I want to find the resistivity, I could solve for it through this equation. It is equal to the resistance times the cross-sectional area over the length. They say that we have a ruler, so we could measure the length of the element and the diameter of the cylindrical circuit element, so we can compute both the cross-sectional area and the length. As for the radius, well, we could just use Ohm's law. We can graph voltage versus current. R is equal to V over I. And so we could essentially use the slope of a voltage and current graph to find the resistance, and then we could eventually plug all those into this equation to find the resistivity of the circuit element. How would the collected data be graphed? Well, I think I just answered both of those. So we adjust the voltage of the, up here, it's a variable power supply. We can adjust the voltage of the power supply and measure the current through the resistance, the resistive circuit element, to calculate its resistance. So they actually end up doing an experiment here. Experiment 2, the students are asked to use a graph to determine the resistivity ρ2 of a solid cylindrical resistor made of the same material but different lengths. The cross-sectional area is this quantity given to us. The students directly measure the resistance between each ends of the resistor. Here's a table. Indicate two quantities measured from table 1 or additional calculated quantities that could be used to produce a straight line that can determine ρ2. Well, again, we could use the resistance equation involving resistivity. Resistance is equal to ρ2 times L over A, over cross-sectional area. We have cross-sectional area, we have the length, we have R, we have everything we need to solve for ρ2. ρ2 is equal to, again, resistance times A over L. So what can we plot? Well, the way you want to think of this is this has something to do with the slope, where the slope is equal to the change in the y over the change in the x. If I want to find the resistivity, you could see I have R on top and L on bottom. So R should be plotted on the y-axis and L should be plotted on the x-axis. Now, what is R over L equal to? Well, if I solve for R over L, that's the slope of this graph. That's going to be equal to ρ2 over the cross-sectional area. So that's how I would derive an expression, or I should say a quantity for ρ2, is plot L on the x-axis, L on the horizontal axis, and the resistance on the vertical axis, and then have, take that slope, set it equal to ρ2 over A. That means that ρ2 is just equal to the slope times the cross-sectional area if I multiply A on both sides. So on the grid provided, create a graph that could contain all these quantities, or that would contain all these quantities. So I'd say, what do we plot on the x? Length on the horizontal, so length in meters, and then resistance in ohms. Go ahead and plot these. I'm not going to go ahead and waste my time doing that. I assume you know how to plot a simple graph like that, but you'd plot all. Make sure that you list your like your markings on the axes. You would draw a line of best fit, something like this. Find the slope, and remember, in order to find the resistivity, we take that slope and multiply by the cross-sectional area, which was given here. Using the line of best fit, calculate ρ2. So ρ2 is equal to the slope that we got here. You would just measure what the slope is and multiply by the cross-sectional area, which they said was 5.10 times 10 to the negative 6 meters squared. Lastly, question 4, long parallel wires, S and T. Okay, so when I think of long parallel wires, this is probably some kind of magnetic force problem between them. They're a distance 2 apart. Both wires carry equal currents I, but the currents are in opposite directions. Both wires are equal and parallel to the x-axis. At the instance shown, they are distance sphere 1 up here is distance d above wire S, and sphere 2 is distance d below wire S. And both spheres are moving with speed v in the x direction. Each sphere has charge plus q. Okay, so there's a lot going on here. We have moving charges and a couple of wires. F1 is the magnitude of the magnetic force exerted on sphere 1 due to the currents in wire S and T. F2 is the magnitude of magnetic force exerted on sphere 2 due to the currents in S and T. Indicate whether F2 is greater than, less than, or equal to F1 by writing one of the following and justify your answer. Well, notice that they say force exerted on sphere 1 due to the currents in the wires, only the wires. So we have to use the formula for the magnetic force from the wires. So if you remember, the magnetic field for a wire is mu naught I over 2 pi r. That's for any wire with current going through it. And then how do we actually find the force? Well, we're finding the force on a essentially point charge, which, if you remember, the magnetic force is equal to Q B cross B. So that's essentially going to be, both of these have plus Q, that's pretty easy to discern, times their velocities, which are the same. So those are, we've got to be looking for what's different between the two. And then basically the sum of the magnetic fields, which is going to be like mu naught I over 2 pi r. So what's different between them? Well, they're equidistant from the wires. Actually, this one's equidistant from both wires. This one is not. Just to keep that in mind. The greater the distance, the weaker the magnetic field, and the weaker the force. So let's go ahead and take a look. This can be essentially done conceptually. So if you use the right-hand rule, this means that wire S, it's going into the page down here and then coming out of the page here. The magnetic field for the other one's going into the page here. So essentially both of these, anything above is going into the page for wire T on the bottom here. It does get weaker as you go away. And then it's going to be going out of the page down here. This one's going to be the opposite. It's going into the page below, out of the page above. So note that for sphere 2, these magnetic fields are going to add constructively, because for wire T, it's going into the page, and for wire S, it's going into the page. Both magnetic fields are going into the page, so they will add together, creating a stronger total magnetic field and stronger magnetic force on sphere 2. As for sphere 1, not only is wire T further away, so its magnetic field is weaker at this point up here, but it's also going into the page, whereas the magnetic field from wire S is going out of the page. So they subtract, which leads to a weaker total magnitude of magnetic field and therefore magnetic force at that location. So we can say by that explanation that force 2 is greater than force 1. You can give a couple of reasons for your explanation. They're working together. They're going in the same direction at location sphere 2, whereas they are subtracting to make it weaker at sphere 1. You're also further away from wire T. This one's equidistant from both wires. Derive an expression for the magnetic field total at the location of sphere 2 due to currents, wires S and T in terms of d, I, and physical constants. So as I mentioned, this is the equation for the magnetic field produced by a wire with current in it. These are both going to be the same thing because they both have the same current I and they're both equidistant. So I'll have two of them. And what is the, oh, they just want B. Okay, so that should be simple. It should be mu naught I over 2 pi d plus mu naught I over 2 pi d. They're both going in the same direction and they're identical, so they add. So that just gives you mu naught I over pi d. You just double this quantity, meaning the 2's cancel. Mu naught I over pi d. Oh, that's the last part. Later, wire T carries current 3I in the x direction. So now the currents are not equal. Looks like the rest of the configuration is the same. Determine whether F nu is greater than, less than, or equal to the original F2 that we got here. Or we said the currents are adding together. Oh, actually, look at this. Not only do they increase the current in wire T, but they actually reversed its direction. So now they're actually going to be working against each other. So if you do the right-hand rule, this is now coming out of the page from wire T, and it's 3 times stronger. Whereas this one for wire S is still going into the page, so they are going to actually subtract. So I'm essentially going to have mu naught 3I over 2 pi r minus mu naught I over 2. So they're subtracting, and one of them is 3 times stronger. That actually leads to us having 2 mu naught I over 2 pi r, which is again, or I should say d in this case, which is mu naught I over pi d. So we actually get the same magnitude as last time. The only difference is it's going, I believe, in the opposite direction, because first the total magnetic field was going into the page. Now the total magnetic field is going to be coming out of the page, but it's equal strength. It's equal and opposite. So the magnitude of F nu is actually equal to F2. You still essentially have the magnetic field produced by 2I. First we had I and I, so we got 2I. Now we got 3I minus I, which is still 2I. Same strength in both cases. So that's the end of the exam. Let me know your thoughts, questions, feedback in the comments, and I hope to see you in the next video.